Thanks for coming to our talk, Tune Your Way to Savings. And I didn't even get the bird pun in there, tune, so that's awesome. Okay, so the focus of this talk is a project that Brian and I worked on. The goal of the project was to reduce the operational cost of running the Twitter ad server. The ad server is our revenue engine. It performs ad matching, scoring, and serving at an immense scale. The optimizations that we discovered in this project enabled us to save a lot of money in running this system. And we'll tell you about how we achieved this over the course of our talk today. So a little bit of background about us. My name is Sandy, and I'm an SRE at Twitter. I've been there for about 3.5 years. I've been working on the ad serving team for about 2 years. The ad serving team is responsible for building, maintaining, and operating the systems that serve ads on Twitter.
Cool. And I'm Brian. I've been a Twitter storage SRE for almost 3 years now. I have a focus on benchmarking and performance optimization, and am the author and maintainer of RPCperf, which I open sourced at Twitter, and that's a benchmarking tool. Great. So just to give you guys some context about how we're going to cover this talk, we're going to give you an overview of the ad server and our goals. We're going to talk about how we got started on this optimization effort. We're going to talk about our experiments and analysis, as well as touch on post-launch care and feeding. And then we'll wrap up with some insights and our conclusions.
Okay, so let's start off with an introduction to the application that we're actually working with here, as well as an overview of what our goals were for this project. So who here has worked with an ad server before? Oh no, more than I was hoping. Okay, no eye contact. Okay, great. This is exciting. So I'll have some good questions at the end. Okay, so at a high level, a client ad request comes into the front end ad server. And then the front end fans this request out to multiple backends. The backends then determine what is the best ad to serve the user. And then they return a selection of ads to the front end. The front end makes the final selection of ad based on, what is the best ad to serve the user, and then returns the ad to the client. So the front end ad server is network bound because of that fan out portion, right? The fan out operation it has to do. And the back end ad server is CPU bound because it does a lot of computationally heavy operations. So to go into a bit more detail, which is going to follow the diagram you see here, when the backend ad server receives a request from the front end, the first thing it's going to do is go through the selection stage, where it selects viable ad candidates. And this could be anywhere from tens of ads to thousands of ads. The second thing it's going to do is perform lightweight prediction. And it does that to narrow down candidate ads while considering the question, how likely is this user to engage with this ad? The lightweight prediction stage decreases the number of candidate ads for which the CPU-intensive heavy prediction work must be done in the next stage. The more candidates that we eliminate in the lightweight prediction stage, the cheaper the request is in terms of CPU and latency. However, fewer candidate ads can also mean that we return a slightly lower quality ad. So after the lightweight stage is done, the backend ad server is going to do the CPU-intensive heavy prediction on the remaining candidates to identify the very best ad for that user. And then the fourth thing it's going to do is a full auction, and it runs that auction on all of the candidates that survive heavyweight prediction. And then it's going to find the ad that it thinks is best and return that ad back up to the front-end ad server. And the front-end ad server is getting these best ads back from all of the backends that it had previously fanned out to. Once the desired candidate reaches back up to the front-end ad server, the front end is going to perform a secondary auction to find the optimal cost per impression for the advertiser. So we want to strike a balance between serving the best ad for the user while also providing the best possible value to the advertiser. Once that secondary auction is complete, we return the winning ad to the client.
Cool. So let's talk a little bit about the environment that we're running in. At Twitter, we have a very large shared Mesos infrastructure. For those of you who aren't familiar, Mesos provides an abstraction across the resources within your data center, allowing you to schedule your job across all the resources available. In a shared environment, this might be a mix of platform types, maybe a mix of networking speeds. We also have this concept of hybrid mesos, where basically you get your own small mesos cluster dedicated to your use case, and you might be able to make some different trade-offs with something like that. We'll go into that in more detail in a bit.
Thanks, Brian. So let's talk about this mechanism that exists in the ad server system. To ensure that our desired success rate is maintained, the ad server uses concepts from control flow theory. We have a basic controller with a feedback loop to continuously learn the appropriate value for a control variable that is defined by us. We define success rate as the ratio of requests received to ads served. And the primary factors that affect our success rate are CPU utilization and latency. So let's review the function of a basic controller really quick. So a basic controller keeps a system at a desired set point. In our case, desired set point is a target success rate that we've specified. And it does this by continuously calculating the deviation of the process output, and that is the current success rate, right? That's what the system is outputting. So it's calculating the deviation of the process output from the set point and minimizing error, which is deviation from set point, by adjusting the value of a control variable. So let's talk about this in the specific context of the ad server. We fix our set point to a target success rate of, say, 99.9%. Our controller will constantly track towards this target success rate by adjusting our control variable. And in world of ad server, this control variable is called adaptive quality factor, or QF. And QF tells us roughly what is the level of quality of the ads we are currently serving. So when QF changes, the ad server adapts its behavior to change how it uses its available resources. The purpose of this is to make sure that we will still be able to serve ads during times of high load, even if it means the quality of those ads might be slightly lower than it would be under lighter load. So the reason I'm going over this part is because this actually makes performance tuning harder, because it means ad server is continuously adapting to the changing conditions in its resource availability due to load. Right? This makes it difficult to get an accurate baseline of performance, and it also makes it so that you cannot easily see the specific impact of performance tuning in isolation. All right, so let's go over the key metrics that we picked, right? Because you need to know, well, if I'm going to do this performance tuning, what am I going to look at to know whether or not it's working? So there's 3 metrics that we picked: quality factor, QF, latency, and RPMQ. QF, as we said previously, is a rough measure of the level of quality of the ads we're currently serving. And that relates back to how well the system is using its resources. So performance tuning will affect quality factor. Latency is affected by CPU and network and directly impacts success rate, which drives the feedback loop that modifies QF. So performance tuning will affect latency. RPMQ is a window into how much revenue is being made at a given time. So this can be higher or lower for a number of reasons, including QF. And we also need to make sure that RPMQ is not adversely impacted as a result of the performance tuning that we're testing. So we compare this metric in our experiments against our control. So what does this mean for the system and for revenue? Well, in general, when load is higher, latency is higher, and QF will adapt downwards to maintain target success rate. You can see this on the top chart, right? You can see quality factor, the orange line, kind of dips down a bit. When load, the blue line at the bottom, peaks up, right? So quality factor is adapting down to compensate for the heavier load to sustain the target success rate of 99.9%. Practically speaking, lower quality factor means that fewer ad candidates are being subjected to the heavy prediction phase. The resulting impact is that while we are still able to return an ad to the client, which keeps our success rate high, the quality of the ad is not as high as it would necessarily have been under lighter load conditions. So that could mean that RPMQ is lower. It's also important to understand that the monetary value of queries is variable, right? So the cost of a failed query also varies. One observation that we have is that more monetizable queries are more computationally expensive and therefore higher latency. So these queries have a greater number of candidate ads in the auction. That means those candidate ads have had to go through heavy prediction, which takes longer. And this means it is more expensive from a resource standpoint. So in conclusion, the more work that we're able to do for a query, the more money we stand to make. And to reiterate why this makes optimizations hard, the adaptive nature of this system, coupled with the constantly changing QPS load, both in terms of volume of QPS as well as the weight of the queries in question, makes data analysis difficult when experimenting with performance tuning.
Cool.
All right, so let's review what is our hypothesis and our goals. All right, our hypothesis was that if we had more control over how our resources were used, then we could use them more efficiently to do more work with the same amount of resources and therefore do an equivalent amount of work with fewer resources. Our goal was to reduce the overall resource footprint of the ad server, thereby reducing the cost of operation. A constraint on this is that the performance of the ad server, both in terms of the volume of ads served, success rate, and the quality of the ads served, QF, must not be adversely affected by these changes. So why were we bothering with this? Like, what is the point, right? Well, this is a very, very large deployment. So we're talking a lot of resource reserved for this service to operate. Even small efficiency gains, especially in terms of reducing CPU reservation, can result in large savings. Some of the secondary benefits to this project are that, if we're able to modify our deployment in such a way that we reduce the number of containers, we reduce the amount of load on some of our downstreams. We reduce the amount of logs being written, the amount of metrics being written. And that can also take some of the dollar amount off of our operational costs.
Cool. So how did we start on this project? Well, first, you need to assemble a team. In this case, we created a virtual team to look into tuning the ad server. And we determined we needed people who were familiar with the service, like Sandy, as well as engineers who could do analysis of the software itself, so the software engineering team. And we also wanted to involve folks who could actually do deep analysis of how the service is running on the actual hardware platform. So we pulled in some folks from hardware engineering as well. Now that we have a team, we need an environment to test in. So we provisioned enough resources to run one cluster of both the ads front end and the back end service. So when we did this, we purposely selected a SKU with high-speed networking. Since we chose a homogeneous platform for this, we were able to change some of the assumptions that we had to live with in the shared environment and remove restrictions that we had for mixed speed and platform clusters. We also theorized that we'd be able to tune these applications specifically for this platform.
Okay, so as we started to approach how to go about testing this, we knew that there were a couple things that we could change at the high level. One category of things we can change is container shape, right? So we can change container shape either by shrinking the container and sharding wider, more horizontally. So that involves reducing the number of CPU per container and increasing the overall number of containers. The other way that we could change container size is to use taller instances. So that is, give each container more CPU and shrink the overall number of instances. In both of these cases, we had to look at how does container sizing affect system performance, right? So how does QF behavior change with more or less CPU resource, assuming that the QPS to CPU ratio is the same? One thing to note, so a second category of high-level things we can change in hybrid Mesos is resource isolation. In the shared Mesos environment, resource isolation is enabled to prevent resource-hungry services like the ad server from being bad neighbors, so that co-tenant processes aren't starved for resources. So for the ad server backend, we knew it was CPU bound, right? So we wanted to look at removing CPU throttling. If you guys have worked with Mesos before, you probably know that it uses CFS to achieve CPU isolation. Since ad server backend is CPU heavy, it sort of falls into scenario C down here, which I don't know if you guys can see that, but I pulled this from the Mesos documentation. Basically, it's showing that, assuming a heavy request has come into the ad server backend during the second interval on the chart, and all of the CPU quota is consumed within the first 25 milliseconds of the interval. Well, that means that CPU is throttled for the remaining 75 milliseconds of the interval. And the compute for that request or any other request that might come in at the time, cannot be provided until the next interval. So this presents a problem. This causes latency to go up, right? Because we're waiting for our CPU resource to become unlocked again. For the ad server front end, we looked at network egress limits because we knew the front end is network bound. So network egress limit is limited in the shared Mesos environment, again, to prevent bad neighbors. So the ad server front end egress bandwidth actually stays well within the egress limit, but the problem is it's extremely bursty, right? And that's because of the fan out that it does. So bursty network egress is penalized in shared Mesos by queuing discipline as well as in the form of dropped packets. And again, this increases the overall latency of the system. And what does increased latency do in the system? It causes QF to decrease. So that's bad.
Cool. So since we're running in a hybrid Mesos for this experiment, there are some lower level changes that we now get access to. Through specialization of the infrastructure, we gained more control. We can take control of scheduling within the server, restricting our process to run on certain cores. We can even try things like huge page configurations that weren't possible in the shared environment. We could also do things at the BIOS level to sort of change the performance and power save balance of the hardware itself. Again, so this is not an exhaustive list. There's so much more that we can do here. But the key point is these types of tuning are harder to achieve on a generalized shared infrastructure, but can become available when we specialize.
All right, now let's shift gears a little bit to talk about how we designed and executed our experiments and how we analyzed the resulting data. So as mentioned previously, moving to hybrid Mesos allows us to select for a different network speed and also gives us the freedom to disable resource isolation on CPU and network egress. So based on what we know about how the ad server works, we hypothesized that disabling network egress would reduce latency for ad server frontend, and disabling CPU throttling would reduce latency for ad server backend. Both of these changes together could have a positive impact on the overall ad server performance because of the reduced latency. This would enable us to maintain our target success rate without QF needing to be adjusted downwards. Here you can see the result of what happened when we disabled the network egress limit on the ad server front end. The blue line is the experiment cluster, as they're labeled, and the orange line is the control. So when we removed the network egress bandwidth limit, we saw that the application was able to make use of the new bandwidth available to it, right? So in this chart, we see that egress bytes per second is about 10% higher after the limit is removed. And then here, this is more interesting, more relevant specifically to reducing latency. You can see this metric is a latency metric for the ad server front end. This latency is the amount of time it takes round trip from a request to depart the front end and return from the back end. So after disabling network egress limit, we saw P99 and P999 reduced by about 20%, which is great because that means the overall latency in the system is lowered and QF can be higher.
Cool. So now let's talk about huge pages. Well, first, what are huge pages? Well, when memory is allocated, it's allocated in a unit called a page. By default, these are 4 KB sizes. Some of this is architecture dependent, but x86 64 here. When we're addressing large segments of memory, the number of pages to represent that memory space increases. This incurs overhead as we need more entries in the TLB, the translation look-aside buffer. Excuse me. By enabling huge pages, we can address the same amount of memory with fewer entries in the table. So we wanted to try what 2 meg or even 1 gig huge pages looked like for us. One of the trade-offs that we made when we selected for 1 gig huge pages is that those need to be allocated at boot time. So there's a little more configuration that needs to go into this. Yeah, basically our hypothesis here was that with our large heap size, we'd see some gain by having fewer entries in the TLB to represent the same amount of memory space. So we configured the backend service to use 1 gig huge pages. And here we can see we deployed our control and experiment at the same time. We left the control with the 4K page size, and our experiment cluster has the 1 gig page size. So during the deployment, you can see that these things kind of track similarly. This is due to the adaptive nature of QF. However, once that feedback loop stabilizes, we can see that our experiment cluster has a higher QF than that of our control. So this indicates to us that the backend has become more efficient and is able to produce a higher quality result with the same amount of resource. In this case, with this change, we gained over 15% on QF by enabling 1 gig page size. Okay, so now NUMA. So this is sort of where reality of the platform that you're running on starts to hit you. So what is NUMA? NUMA is non-uniform memory access. What this means is that some of the memory is closer to one socket or one CPU than it is to another. Memory access times, latency, vary depending on what set of DIMMs have the RAM that you need access to. Local access is faster, while foreign access has to traverse the QPI link between sockets. Our selected platform was a 2-socket system, so we have 2 zones, each with half of the physical resources of the server. And below that, I have NUMA stat output. The first is for a process that has not been pinned. So the scheduler is just doing its thing, and it's allocating memory according to the policies of the OS. And we can see there that we get about a 10 gig and 8 gig split, so it's not even balanced. Below that, we see what happens when we use NUMA CTL to pin the process to both allocate and execute within a single NUMA zone. So we can see there that basically our entire Java heap of 32 gigs in this case is allocated all on node 1, which is also where the process will run. So this should give us better locality for the memory access. We won't have to traverse the QPI link. So what did we see when we tried this, right? So we totally eliminated foreign memory access. So 10% of our memory access was foreign memory access previously. We also saw improvements in our L1 cache behavior. So previously we were spending 60% of our clock ticks on L1 access, so pretty L1 bound here. However, once we enabled the NUMA pinning, we reduced this to just 15% of the clock ticks, which is a total savings of about 75% in terms of the L1 access times. We also saw an improvement in cycles per instruction, or CPI. Basically, this is a metric that is a measure of the efficiency in terms of execution on the CPU itself. So lower is better here because it takes fewer cycles to run the particular instruction. So here we saw a gain of 20%, reducing our CPI from 1.54 to 1.23. So these are some nice wins that we got by pinning to a specific NUMA zone and only running there. Cool. So our results with NUMA pinning, they look good, and it led us to a couple of questions, though. So how will changing the process layout impact the efficiency of the service? We saw the benefits with NUMA pinning, but could we gain more control by pinning threads to specific cores? Secondly, we're going to need to answer the question of how many instances we could run on a single server. If we allocate all the resources within that server, this sort of determines the possible shapes for the ad server jobs themselves.
Yeah, so when we first started testing to see can we use all the resources on the server, we settled on a size of 4 instances of ad server backend at 14 CPU per instance. So with that setup, at this time, we did not actually have any mechanism to allow us to pin multiple instances to specific threads on a single NUMA node. So in the 4-pack setup, we saw from NUMA stat data that the two instances tended to live on a single NUMA node, but they behaved very badly, right? We could tell looking at our application metrics that the interference was pretty bad and it caused severe performance issues. So, well, why was this? Well, we inferred from looking at the NUMA stat data as well as the application metrics in the hybrid Mesos environment, and then looking at how the service ran in shared Mesos. We inferred that ad server backend exploits the flexibility of CFS to steal available CPU threads when it needs to do bursts, right? So basically, in terms of ad server backend, the need to burst CPU is very frequent because we have different weights of requests coming in all the time, right? You might get really cheap requests coming in, everything's fine, and then boom, you have a heavy request and you need as many threads as you can. So Ad Server Backend will steal as much of the CPU threads that are on the box as it can. This is the behavior that is encouraged by the controller feedback loop. And 2 Ad Server Backend instances occupying a single NUMA node appeared to result in all threads being occupied at all times. So there was no available thread capacity to burst into. So you think, well, okay, well, why aren't we seeing the same problem then in shared mesos? And yeah, we sometimes do. It depends on who the other tenants on the box are, right? But typically, most of the other services running in the shared mesos environment are not as CPU greedy, right? So they're not using their threads. And Ad Server Backend will steal its neighbors' unused threads when it needs to, which is frequently, and CFS allows for this to happen. So in conclusion to that, it seems that the 2 backend instances running on a single NUMA node were stepping on each other in direct competition for the same set of threads.
So kind of to avoid that, we decided to give each instance an entire NUMA zone worth of resources, so we'd run 2 on a box. This naturally resulted in a larger instance size than what we had on our shared infrastructure, but a net reduction in the number of instances to represent that same amount of CPU and memory. So for the same amount of aggregate traffic coming in, each instance is going to need to handle more QPS. Additionally, we'd also have a significantly larger Java heap to GC over.
Okay, so we ran a bunch of different experiments as we were doing all of this testing. We give you an idea, over the course of this talk of a few of the experiments that we ran and what some of the data were from those experiments. But we actually ran over 60 different experiments, testing different config values and different permutations of our tuning. Experiment duration ranged from anywhere from hours to days. And we often needed to repeat trials when data was inconsistent or couldn't be explained. So thoughtful experiment setup is really important. Make sure that you understand what variables you're changing, and ideally only introduce 1 new untested variable per experiment. Because if you're introducing a bunch of variables, you might think, oh, I'm saving time, but you're not. You're going to have to go back and test them independently. So just do it up front. It's easier. Tracking your experiment setup, so start time, end time, and what was my server configured to do in this experiment. Tracking that data is critical for being able to analyze data after the fact. And this is just an example of a spreadsheet that we use for tracking. We sort of track you can see start and end there, and then we have the fine print as our experiment setup, and then notes that we observed, as well as links to dashboards. This is really useful. Yeah, this is really useful, especially because you're dealing with a distributed team, and everybody kind of drops in and looks at a graph when they have a few free cycles to do it. So ideally, when you're doing your data analysis, give everybody time to look at the data, and then and this is what we did, is try to get the stakeholders in the room. So we have stakeholders from software engineering team, the hardware engineering team, and site reliability engineering, right? So myself and Brian and some SWEs and some hardware eng. And then with a combined knowledge of these 3 skill sets, it will enable us to interpret the results of an experiment and assess how the application has responded to the changes that your experiment introduced to the hardware or the config settings. Okay, so once we had identified what our final desired configuration was, and we felt like, okay, we've gotten some good wins here. We could get more wins, but we could keep going forever. We could keep chasing optimizations forever if we wanted. So we decided on a configuration we wanted to roll out to production, and then we started thinking seriously about what long-term maintenance needed to look like. So making the decision to move to hybrid mesos is not something that we took lightly. It involves a long-term commitment and to ongoing operational work. It involves long-term debugging and experimentation. The work is never really done here. And service owners have to assume some additional responsibilities that used to be handled by specialized infrastructure teams. Right? You're now thinking about a lot of things that you weren't thinking about before. So some of this stuff is easier than other parts of it. The easy part is to make sure that you're working with the relevant teams that are involved in provisioning and setting up new hardware to spec. So make sure you have your hardware pipeline. And make sure that you have correctly integrated your config changes according to the standards required by the team that owns CMS. So if you're on Puppet, for example, make sure that you've added the correct values to the playbook, set up new playbooks if you need to, and make sure that you test those config changes, that they behave as expected under conditions you plan to operate under, right? So if you aren't sure whether the box gets kicked at the end of the Puppet run or if it needs to get kicked at the end of the Puppet run, make sure you iron that detail out early on. Otherwise, it's not a fun surprise. So the harder part of the ongoing operational work is that you're now forever going forward playing in a non-standard sandbox. And your application may not adapt the same way or as well to changes. You have to really be on top of this, and the work is ongoing. So you're always going to be thinking about it a little bit. You may find performance regressions either due to a software regression that previously would have been masked by the safety of the shared environment, or maybe a new load condition that presents itself in production, a load condition that didn't exist when you were doing your testing and you couldn't test for because you didn't know it was a valid case to test. So those things come up. Also, you'll now most likely want to integrate testing new operating system releases and new hardware platforms into your to-do list, whereas for a service in the shared Mesos environment, the bulk of this work is shouldered by other teams. And you'll always want to be on the lookout for opportunities to continue running experiments that can help you identify new optimizations for your system.
Great. So what did we learn through all this? We have a couple of key insights and takeaways. Production is very different from a sterile lab environment. The complexities of production systems can make it challenging to untangle the effects of your changes, especially when you have multiple clusters load balanced together and a service that reacts dynamically to changes in traffic patterns and volumes. You will make mistakes, you're going to have some false assumptions, you're going to get some things wrong. Have a plan for when that happens. And be sure that you're always documenting and sharing what you've learned so that other people within your organization can learn from what you have.
Yeah, shared knowledge is something that really, I think, not just in projects like this, but everywhere in SRE is something that we can all do more of. It's hard sometimes, but the value really pays off over the long term.
Absolutely.
So another thing that is sort of a takeaway from this is the importance of staying focused on the metrics you're trying to move. It's good to identify the metrics that you want to move up front before you start running experiments. So over time, we picked out QF, latency, and RPMQ right away. We're like, okay, these are the ones we care about. And as we started to ramp up on our experiments, we realized that there were a bunch of other metrics that caused the metrics we care about to change. And so we start looking at those metrics. And then instead of looking at 3 things, we're looking at 30 things. And that's fine. But ultimately, as our experiments get more sophisticated and we understand more about how the system is responding to our tests, we converge back down onto a smaller subset of metrics. That's going to help you stick to your deadlines, right? Holding your team accountable to stick to these metrics that you've agreed are useful for the purposes of the project is also a huge time saver. Otherwise, people go down rabbit holes. You get somebody who's really excited about something they see on a graph, and they want to go chase it, and they spend half a day running some experiment that maybe isn't even useful based on a false assumption. So, sticking to these metrics will help you keep your project on track and help you ship on time. If you get outlier test results, because that's sometimes it's going to happen, you're going to run an experiment and you're going to say, oh, this one looks very different from the previous 3. Well, rerun the test, conduct another trial. This is more efficient than chasing down outliers because you can spend hours or days chasing down outlier results. Other thing you want to do is resist confirmation bias, right? Be wary of seeing a change where there isn't one or drawing an invalid conclusion from the data that you see, especially if it looks favorable. After doing a lot of experimentation for a week or maybe 2 weeks and hitting a bunch of dead ends and getting pretty frustrated, you really just want to hear some good news. You want to see some good news. And it's really tempting to sort of think, oh yeah, this one looks better than the last one. But it's probably a trap. As it turns out, this stuff is actually really hard to get right. And there's not much low-hanging fruit. And anything that looks easy is still going to come with its trade-offs. So be thorough and take your time.
Cool. You should always be using data to drive your decision-making process when you're doing something like tuning or optimization. But in order to do this, you need to be able to clearly communicate to your audience and share data at the right level. What seems like interesting detail to share with other engineers might be too detailed for higher level executive summaries where metrics like dollars saved matter a lot more. Well-presented data should make the case for if a proposed change is good or bad and provide clear technical evidence to get consensus from the engineering teams.
Yeah, that's really important because if you go in with a ton of data, people kind of, the eyes glaze over and they aren't really listening anymore. And if what you're trying to get out of that meeting is a decision on how to move forward, you need to keep it as concise as possible. All right, so it's also really important to be fully aware of the cost of continuous tuning efforts. So how much engineering resource will your ongoing tuning efforts take and your ongoing maintenance efforts take? That must be weighed to determine if the additional burden of running a custom setup is worth your time. In terms of the payouts of tuning, assuming that you make the same amount of revenue before and after tuning, look at the numbers in terms of were you able to reduce your capacity expenditure percentage such that the cost of acquiring that revenue now represents a smaller percentage of overall revenue earned, right? So you're making the same amount of money, but you're spending less of it to make it. Also think about in terms of secondary savings, where we talked about earlier, reducing the burden on your downstreams, reducing your storage footprint. If you're able to reduce the consumption of downstream systems or writes to downstream systems by reshaping your containers, and you have fewer instances maybe, such as databases and caches that you're no longer talking to as much. That can also represent savings that cuts down your operational bill.
So this one's really hard, setting and sticking to your time estimates and your deadlines. Especially when you're working with a virtual team, you need to plan extra buffer for people to be able to do their day jobs and attend to more pressing issues as those come up. Additionally, when you're doing these kind of experiments and you might need to repeat an experiment that took you a couple of days to run, you need to be sure that you kind of pad your estimates appropriately to account for repeat trials. Be realistic also with how much time the people on the team are going to be able to dedicate to the effort. These things take a lot of time and a lot of focus, and you might not always get as much time to work on this as you want. Also be sure that you're sticking to your deadlines. You want to always be sharing your results early and often with the team that you need to get consensus from. So some conclusions. Well, Sandy and I found this work has a lot of unique and interesting challenges, which really push the depth of your own personal knowledge. It's a great opportunity to work with other engineers with different focus areas and think about all the layers of the stack and how the software is interacting with your physical hardware.
Yeah, it's actually a really, really fun project. A lot of times I'm really focused just on my team services, so getting to work with people from other teams and actually think about hardware instead of just containers was pretty fun. So some other things that we learned, well, the benefits, well, plus learning, the benefits of these efforts manifested in the form of savings. So these optimizations that we discovered through this testing enable us to save a lot of money. CPU reservation was able to be decreased by 6%. Our initial estimate was 17%, which was a lot more exciting, but that was the lab estimate, and lab does not equal production, and 6% was the right number. So there you go. Still a lot of savings. Also, we reduced reads and writes for certain downstreams by more than 50%. Also great. So all of this stuff factors into savings on our operational overhead. In terms of metrics improved, we did substantially improve quality factor. However, that's only for certain scenarios, right? You know, quality factor fluctuates based on resources and based on latency. So now we have a different set of challenges, essentially, and we're still learning, oh, why does QF behave this way over here, whereas before it was more resilient under this type of load, right? So these are things we continue to investigate as part of our ongoing experiments.
Yeah, so what's next for this project? So we talked about NUMA pinning and CPU pinning and how we didn't really have a mechanism to pin within a specific NUMA zone. So we developed a tool that's going to allow us to do that. Will our 4-pack experiment work better if we gain even more control over the scheduling? These are hard problems, and we really want to continue to explore and learn more about this.
Yeah, and we're currently working on testing a newer hardware platform, which has even more cores and faster processors. So we're interested to see how Ad Server Backend is able to utilize these additional threads. A couple of resources for you guys. One is the Resilient Ad Serving at Twitter Scale blog post, which came out last year. A lot of the info that I presented at the beginning that talks about ad server architecture is from that blog post. So there's more there to read about. There's a lot of really interesting stuff. The system is actually really interesting in terms of how it works. So definitely check that out. Another resource we found useful early on was there's a clarifications on Linux's NUMA stats blog post that's kind of a little bit like a missing manual type of deal. So if you're working with NUMA stat, check it out. Might have some useful data. And of course, Systems Performance book by Brendan Gregg. Definitely use that.
Yeah.
All right, so if you'd like to learn more, chat more about our optimization projects, we're actually hosting a Twitter SRE open house at headquarters over at 9th and Market on Wednesday evening. So if you're still in town after SRECon and you want to learn more about what we're working on, Brian is going to be presenting on his RPC Perf open source tool, which is a tool for benchmarking RPC services. So, I don't know if this will work. Hopefully it will if you can snap the QR code and it'll take you to the Eventbrite link. Okay, questions?
Nope, you beat me to it.
Oh, darn it. I thought people had questions. Gosh. Okay, that's all right.
Great talk, thank you.
Yeah, thanks for coming.
Thanks.
I was wondering how you gathered the metrics around CPI and L1 ticks with the NUMA pinning.
Yeah, so Mesos, the Thermos executor, actually collects a lot of detailed stats like that from perf, so the Linux perf stuff. So for us, that's exposed in our monitoring, and we're able to track those metrics within our Mesos job, essentially. So we get a lot of that for free just through Mesos and the kind of stats that it exposes for us. We also used Intel vTune to get some of the more detailed information about like our L1 cache efficiency and stuff like that. So a couple different ways to look at it, but basic stuff, perf works great.
Rick Farrow, I was fascinated by the 1 gig pages. So does that mean that everything in that cluster is now configured with 1 gig pages?
Yeah, so what we did is we set aside a certain percentage of the memory within the server to allocate to the 1 gig pages, because you can't do transparent huge pages with a 1 gig page size. You can only do 2 meg if you want to allocate at runtime. So you actually need to specify in your kernel boot parameters that you want this many pages of a 1 gig size and reboot the machine for that to take effect. So we kind of measured how much we thought we were able to give to our service, and so that's what we did there.
It still seems 32 gigs for the ad server, maybe 8 gigs for the rest. Anything else that's going to run on the machine, so it's pretty heavy and balanced.
Yeah, we definitely had to maintain a balance there. I don't know off the top of my head, but maybe we allocated somewhere around 80% for the application and left the remaining for the OS and monitoring software and other things that need to run there, like Puppet and stuff like that.
Okay, hey, thanks.
So I'm really interested in the process that you followed for defining your test cases. Specifically, I kind of felt like I was in physics class, right, where I'm being presented with a hypothesis, shown the testing, shown the results. Is that something that your teams have done consistently already, or was that something that you decided to do for this project in particular? Because I feel like you don't see that a whole lot in engineering nowadays.
Yeah. So
so this is something that I enforce in any project that I'm working on that is of this type, because otherwise it's basically wasting everyone's time.
Yeah, and I had done some previous like hybrid Mesos tuning stuff before for our caching services at Twitter, so I already had some hypotheses about what would happen when we changed some of these things. So we kind of started with yeah, just like, hey, we think if we do this, it's going to have this positive effect for this part because it's network bound, or this part's CPU bound. So if we change this, do we see a positive result in our key metrics?
Right. And the other thing to think about in terms of hypotheses is that in scientific method, your expectation is that your experiment is testing your hypothesis, and the expectation is that your hypothesis will be found to be incorrect, right? And so then you iterate on that, and you refine that, and then you go again, and you work towards, trying to find some answers. So we definitely, I'd say we modified these a bunch. We came up with new experiments sort of on the fly, and then waited whether or not they would be worth doing.
Thank you.
Yeah.
So you threw a lot of resources at this. From a purely monetary standpoint, was it worth it, and how worth it, to the extent that you can share, not getting into details, obviously?
Yeah, I mean, I can't give specific numbers, but 6% of our total CPU reservation footprint is significant. It's larger than like a lot of other services are in whole. Like 6% of this service is the size of a lot of other services. So it's a lot. Sorry.
Hey, thank you for the great presentation.
It's size appropriate to the amount of money we make based on that hardware. So
yeah.
You mentioned that removing the limits on network and CPU improved performance. This makes sense, but wouldn't it have knock-on effects on other things running on the machine? Or if there wasn't anything else running on the machine, wouldn't you just set the limits to the physical capacity of the machine?
So there are some overheads that are introduced just in sort of like metering those resources out, and we can talk about this after if you want to go into a lot of detail about like Meso's network isolation, how that's actually implemented. But essentially there are overheads that are there, even if you remove the limit but still have the ability to limit, you still have the isolation enabled without a rate limit, there's still some overhead there.
Well, yeah.
Yeah. So.
Yeah, we should maybe talk more. Unless,
Come find us
Okay.
at the Twitter booth. We can talk more.
Yep.
All right, thank you.
Hey, so I've read several Twitter blog posts from engineers, and it seems that your company is very strongly oriented, for the engineers at least, towards following scientific method when you're looking at making changes. And then even after making changes, verifying, did this actually do what we expected?
Yeah.
And have either of you worked outside of Twitter before?
Yeah.
Okay,
Yes.
great. So would you say that's significantly different from other places you've been? Because from my experience, scientific method is not really applied towards software.
Yeah.
So for me personally, I found that there is a lot more rigor and holding ourselves to a methodology and always verifying than I had seen at previous companies I worked at.
Yeah, I'd say there's also a lot of sort of there's the culture is such that there's freedom to fail, like try things, experiment, and it's okay if it doesn't work out, So people are more inclined to take these risks and do these experiments, and as long as you're being mindful of how you're running it. And what I would say I don't see, at least in my typical work, I don't see as a ton of rigor.
Right.
But I would say I also haven't seen a ton of rigor at my previous companies either.
Right.
So
is that is it a corporate culture of pretty much we expect to see a hypothesis and then we expect to see your results after you've run your test, or is that just...
Not necessarily, but I think, going back to that, data-driven decision-making and communicating clearly, it helps a lot if you spell out, hey, we thought by doing this, we'd see this. Here are some charts that kind of prove this. Here are some secondary charts. So, our key metrics went this way by this much. And now you can have that discussion about whether the trade-offs in terms of maybe operational burden for maintaining this customized configuration is going to be worth it in the long run.
Cool.
yeah,
All right,
what I see a lot of people doing is, or a lot of times engineers will write something that they're calling a hypothesis, but it's not a hypothesis. It'll just sort of be a statement about what they wish was better or different. And it's like, that's nice, but, hypothesis, if you take it back to the most, what they make you do in earth science, right, in high school, is tell you, write it in the form of if, then.
Yeah.
So if I do this, then this will happen. And so I try to bring that back when I write my own hypotheses on things. I try to bring it back to that and say, well, what am I actually trying to test for here, right? And what do I expect is going to happen? And that helps me to focus and limit the scope of my project, because it's really easy, especially when you're throwing like 50 different variables out there.
Yeah.
I worked with a couple different people on this project, and I found that I really enjoyed working with Brian because we had a similar appreciation for rigor in this context. So it was helpful to have like, hey, we're going to isolate these down. We're going to be strict about this, because ultimately, yeah, it saves everybody time.
Cool. Thank you.
Yeah. Any other questions? We have a few more minutes. We could probably take one or two more. No? All right.
Cool. Well, thank you for joining us.
Yeah, thank you.
Feel free to come up and talk to us after.